Hello, this issue shares with you how to build a bodily self-perception model with BrainCog to achieve motor visual associative learning so that the robot can pass the neural test. Combining the result of brain science and neuroscience in the field of self-perception, we proposed a brain-inspired bodily self-perception model. Cognitive psychology experiments have shown that the IPL is activated in response to the movements protected by one's own face and bodily, and the insula is activated in both the bodily ownership and self-recognition experiment. The brain-inspired bodily self-perception model is built around these two areas. In addition, it also includes VPMC and STS. VPMC is used to generate self-motion information, and STS is used to detect motion information in visual field. The IPL relies the motor visual associative learning in the computational model. The IPL contains two areas, the IPLM and the IPLV. IPLM is the area where the motor perception neuron in IPL are located, and the IPLV is the area where the visual perception neuron in IPL are located. The former receives self-motion information from VPMC, where the latter receives visual motion information from STS. The insula relies on self-representation in the computational model. When the agent detects that the motion in the visual field is generated by itself, the insula is activated. The insula receives information from IPLV and STS. IPLV outputs the visual feedback information predicted according to its own motion information, where STS outputs the motion information detected by vision. If both activate the same neuron in the insula is activated. Based on the STDP and the discharge time difference between IPLM and IPLV, the model relies on motor visual associative learning. Finally, a multi-robot mirror test is simulated. After training, the robot outputs the predicted visual motion track in the IPLV based on the self-motion track output by the VPMC. Among the three visual motion tracks detected by STS, the leftmost track is consistent with the prediction in the IPLV, which activates the insula, indicating that the robot believes that the leftmost motion track is generated by itself. The computational model is constructed by BrainCog, including RPL-SN for motor visual associative learning and the insula-SN for self-representation. First, set the number of neurons in each brain area. Then call the cognition and base to build the cognition between brain areas, and then build the brain areas through IPL and insula and the brain area. IPL-SN is built by executing neural model in Node, and uses HTTP in learning rule to complete the learning. The same goes for insula-SN. After building the wolfram work, the network can be trained and tested. In the training process, the VPMC outputs the motion angle generated by itself, and STS1, STS2, and STS3 outputs the motion angle detected by vision. This information is fed into IPL-SN to realize the motor visual associative learning. During the test, IPLV output visual feedback result predicted based on its own movement. STS outputs the detected visual motion tracks STS1, STS2, and STS3. This information is fed into insula, and the visual track that has activated insula most times is considered to be generated by its own motion. That's all. Thank you.